Welcome to 12.4. Today we're going to be talking about angle measure and segment length. Our objective is to find the measure of angles and lengths of segments formed by chords, secants, and tangents. To start out with here, we got a couple of theorems. Theorem 12.13, the measure of an angle formed by two lines that intersect inside the circle is half of the sum of the measure of the intercepted arcs. So to start out with, we've got our two lines that intersect here, and I'm looking for angle 1. So angle 1 is going to be half of the sum of x and y. So the intercepted arc for the angle and the opposite one. So if I add x and y together and take half of that, I'm going to get the measure of angle 1. Theorem 12.14. The measure of an angle formed by two lines that intersect outside of a circle is half of the difference of the intercepted arc. So now we've got two lines that intersect outside of the circle. Okay, so there's our intersection out here. So if we want the angle 1, which is right here, we have to take the two intercepted arcs that are formed by those lines, and we find the difference. So bigger minus smaller, x minus y, and we take half of that. And it could happen in the first picture shown, or it could be as one of the lines is tangent. We do the same thing. We find x, we find y, we subtract them, and we take half of that. Or if they are both tangents, we can still do the same formula. We find y, we find x, we subtract y from x and divide it by 2 to get our measure. Okay, so our first example, they want us to find the value of each variable. We're looking for angle x. Now x is inside of the circle, so that was the first theorem that we talked about. So to find x, we take 1/2 of the sum of the two intercepted arcs. So I add 46 and 90 together, and then I'm going to divide it by 2. Well, 46 plus 90 is 136, and then half of that is going to be 68. So x is a 68-degree angle. Part B, so now I've got two lines that intersect outside. Okay, and I've got a 20-degree angle here. So I'm going to find z. So this one I'm going to use that second formula. So I've got my 20. I'm going to set that equal to half of the difference of the bigger minus the smaller. Now I know 95 is bigger because it's farther away from the 20-degree angle. That one's always going to be bigger. So to solve for this, the first thing I want to do is get rid of that 1/2 so I can multiply both sides by 2. Okay, so I've got 40 is equal to 95 minus z. I can add z to the other side, subtract the 40 at the same time, and I should get that z is a 55-degree angle. Okay, so for these next two, go ahead, pause the video, give those a try, and then when you're ready to go, hit play, and you can see how you did. Okay, so for our first one, example C, we've got an intersection outside of the circle, so we're going to use that second theorem that we talked about on the last slide. So I take the angle of the intersection, which was 70, and I set it equal to 1/2 of the difference between the two intercepted arcs. Now the farther one away is always first, so W is farther away from the 70, so it'll be W minus 110. I solve for W and I get that it's a 250-degree arc. For our second example, D, 35 is an angle inside of the circle, so the lines intersect inside. We're going to use that first formula. So we're going to take the inside angle is equal to 1/2 of the sum of the intercepted arc, so x plus 30. Solving for x, I get that x is a 40-degree arc. Our next example, we've got a satellite in a geostationary orbit above Earth's equator, has a viewing angle of Earth formed by the two tangents. So these lines are tangent to Earth, so they go to the edge. The viewing angle is about 17.5 degrees. What is the measure of the arc of the Earth that is viewed from the satellite? So they want to see this measure here. Well, in order to find this, we need to know what this outside arc is. Okay, we don't know exactly what it is, but we can do it in terms of x, because a whole circle is 360, and I've used x on the inside here, so this outside is going to be 360 minus x. So that's how I'm going to use my formula here. So it's outside of the circle, so we're going to use that second theorem. So we're going to have that angle of the intersection is equal to 1/2 of the difference between the two. So 360 minus x is my bigger arc, and I'm going to subtract the smaller one. Okay, so cleaning this up a little bit, multiply both sides by 2, I get 35. Inside there I get 360 minus 2x. I can add the 2x over, subtract the 35. I get 2x is equal to 325. And then if I divide both sides by 2, I get that x is 162.5, and that's going to be my degree measure. Our second example, the viewing angle of the moon from a spacecraft is formed by two tangents to the moon again, so it's going to be very similar. So we've got our moon, and we've got our spacecraft, okay, and we've got a tangent lines, okay, and then we've got an 18-degree angle here. We're going to do the same thing we did before. So now we've got an 18 is equal to 1/2 of the difference between the two. It's going to stay 360 minus x. Multiply both sides by 2, clean up inside there. I get 360 minus 2x again. Add the 2x, subtract the 36. I get 2x is equal to 324. Divide both sides by 2, and I get that x is 162 degrees. Our last theorem for 12.4, theorem 12.15, for a given point and a circle, the product of the lengths of the two segments from the point to the circle is constant along any line through the point and the circle. So for our first example here, we've got this line here consisting of AB. This line is CD. Those are the lengths. So if I multiply A times B, I would get the same thing as C times D. And for part 2 here, now we got a point outside of the circle. So if I take these two lines, you'll notice how I have to do W plus X, the whole line, times the outside part. It would be the same as if I take the whole line, Y plus Z, times that Y outside part. Okay, and then finally, if we've got a little bit of each here, we've got a line going through the circle from the outside and a line going to the circle from the outside. I can do Y plus Z times Y, and that's going to be equal to T squared. So now when I'm using these formulas, for part A here, find the value of the variable, I'm going to solve for Y. So this one looks like part 2. Okay, so I'm going to set it up just like they do here. I'm going to use this formula, the W plus X times W is equal to Y plus Z times Y. So if this is my first line, okay, 6 is like W, 8 is like X. So if I plug it in just like I see it, W plus X times W, okay, that's going to be the left side of my equation. So now for here, 7 is going to be like my Y, Y is like my Z, so I'm going to have 7 plus Y times 7. Okay, so if I clean this up here, 6 plus 8 is 14. 14 times 6 should be 84. And then if I distribute the 7 into the parentheses over here, I get 49 plus 7y. Subtract the 49 over to the other side. I get that 35 is equal to 7y. Divide both sides by 7. I get that y is 5. For our second example, this one looks like part 3. So I'm looking for z here. I've got my first line. A is going to be 8 is going to be like y. 16 is like z. So I should have y plus z times y again. And then z is going to be like t over there. So it's going to be t squared. So z squared. So cleaning up this left side here, 8 plus 16, and I want to multiply that by 8. So 8 plus 16 is 24. 24 times 8 is 192. That's going to be equal to z squared. If I take the square root of 192, I get that it is roughly 13.9. That's going to be my answer there.